The first seminar of the spring series, 2022. It was about 2 years ago that we stopped doing these things. It's great that things are starting to be different. So how better than to start the series with Pulkit Agrawal. Thank you for coming. Let me cover the basics. So Pulkit is the Stephen and Renee Fincher Professor at EECS at MIT, where he arrived in 2019, and he started the Improbable AI Lab. He has already made an impact with his research and teaching, and I would say especially, even more importantly, with his creative and collaborative energy. Many of us know him, not just because we know who Pulkit is, but because we work with him. And I think that he's already a key connection between many of the labs at MIT. So that's great. Has received several awards, of which I will highlight one, the Best Paper Award at the very competitive conference on robot learning last year, of which I think that you will talk about a little bit today. So that's great. And so Pulkit comes to talk about learning and sensory motor control, something that he has thought about for quite a long time. And with his permission, I'm going to read a sentence from his PhD thesis, from the introduction, which I thought is sort of very adequate to motivate his presentation today. It goes like, evolution took a very long time to evolve the necessary sensory motor skills of an ape, about 3.5 billion years, and relatively very short time to develop apes into present-day humans that can reason and make use of language, about 18 million years compared to the 3.5 billion years. And then he follows, there's probably a lesson to learn from there. So the naive lesson, which I definitely fall prey to quite often, is just to say, well, I mean, sensory motor control is just very hard, right? I mean, trying to get machines to be agile and dexterous like humans is just very hard, and we shouldn't expect that we will not have to work very hard to get machines to do it, which is probably true, but it's sort of in some sense naive. And I think that there's a more nuanced lesson to learn there, which I think that Pulkit captures really well, and his research, which is that intuitively you would think that getting machines to learn to perform really well at much more complex tasks should be much more complex, much more difficult. But that statement points almost to the contrary, right? If we get the sensory motor learning control, or if we get machines to perform well at simple tasks, everything that falls after that, it's almost downhill, right? It feels like it's like low-hanging fruit. So to me, that always has been sort of a dichotomy of is it really hard or is it really easy? And I think that Pulkit's research illustrates really well that point, and has made really good progress in a very short amount of time, which I'm very excited to hear about. Thank you, Pulkit, for making time today.
Well, thanks a lot, Alberto, for the wonderful introduction and taking the time to read a few sentences from my thesis. So, I guess I'll stick to my thesis and, talk about how to learn basic skills for most of my talk, and then see how language can fit in, maybe in the end, for maybe a minute of my talk. So, does anyone has objection if I take off my mask? Nope? Okay. Perfect. So, let's get started. So today, we have legged robots. They are great, right? I mean, they can walk down stairs, walk on many terrains. Right? Here's another example, of the MIT mini cheetah, walking over gravel. Right? But for a moment, let's compare them to locomotion in the wild. Right? So here's an example of a cheetah going down the hill. Right? So if you see the cheetah, its motion seems qualitatively very different from what we saw in the robots earlier, right? It maybe doesn't have any legs on the ground for most of the time. It seems to be in unstable states almost always. Right? So this is what locomotion in nature looks like. And if we compare this back to these robots, they move with all legs on the ground, or at least 2 legs on the ground, right? And most of these robots are actually blind, right? So therefore they can't really anticipate if there's a gap, you need to jump over it, right? So all they're doing is reactive control. So the question is, how do we get from here to maybe something which looks this agile? So of course this has been a topic of great interest, and there have been many works which have been trying to build fast robots, right? So this was maybe one of the examples from Boston Dynamics, which runs really fast. I think it goes faster than Usain Bolt, but it's on a treadmill, right? There's another example from Sangbei's lab, where they built this cheetah, which was jumping over hoops. Again, an impressive feat, right? But then, this robot is limited to the indoor environments, and it needs precise knowledge of the kind of barriers it needs to cross. Right? Now, there are robots also, which can work in the wild. Right? For example, there's recent work from Mark Hutter's group, which shows how we can have like quadrupeds walk on very diverse terrains. But again, if you see these quadrupeds, now they have become really slow, right? So there seems to be a trade-off where either we are able to walk on many, many different terrains, or we can be fast in some very specific terrains, right? And okay, and then here is one more example of a quadruped. This time it is incorporating visual inputs to plan its footsteps. But again, this robot is moving really slowly. So one question you might ask is, why are robots slow? Right? So one possibility is that maintaining stability at high speeds is actually hard. The other is maybe there are some modeling assumptions which are made to write controllers for these systems. Now, what do I mean by this? Right? For example, one common assumption is to constrain the gait of the robot. What do I mean by a gait? So presume, or just look at, like LH means left hind, left front. These are the 4 legs. And these 4 legs, move in a specific fashion, right? So the left and the right, so if you see this leg and this leg, they make contact or not make contact together, right? Similarly, here is another gait, right? So a gait is specifying how the legs of a robot are moving, right? So it's very common that most quadruped systems are assuming a fixed gait. Right? And today we have very good low-level controllers which can convert these gaits into torques to actuate the robot. Then there are other modeling assumptions. One of them is the assumption that there's no slip between the robot's feet and the ground, something we'll look into more detail. Right? Then thirdly, as I discussed, most of these systems are blind. When they use vision, they mostly use it for obstacle avoidance, right? As a human, I also perceive that I see snow in front of me, this is slippery, maybe I should avoid it, right? So that kind of understanding is lacking. And fourthly, maybe there are some hardware limitations to our systems. For example, consider these 2 robotic systems. Both of them have these ball, in their feet, right? Why do they have ball in their feet? Because it makes point contact, right? If something makes point contact, it's easy to model, right? And therefore we can write controllers on top of it, right? Similarly, even the bodies are rigid. So, so what we have done is we have made several hypotheses about what might make agile locomotion challenging, right? And what I'm going to show or discuss is how we have tried attacking these problems. So to begin with, what we set is, our temporary goal is, suppose I am standing over here and I throw a frisbee. can a quadruped, navigate and, go under the frisbee when it is landing? Right? It needs to do it in as diverse terrains as possible. I could be out on a snowy day. There could be puddles in the middle. It has to jump over it, right? So, that's the goal. I throw a frisbee, the quadruped finds its way and reaches just in time. Right? Okay, so, and the main method we are going to follow is that instead of a hand-designed controller, we are going to learn by trial and error. And because we are learning by trial and error, a lot of the training is going to happen in simulation, and then we're going to transfer these controllers in the real world. And here are some teasers of the results I am going to show. Right, so here is a quadruped jumping over gaps. Here's an example of transferring that behavior on the real system. Here is one more example where we managed to achieve the highest speed recorded on the mini cheetah. So it runs at 3.9 meters per second. It can also spin, right? And the good thing is we just don't have to be in the lab. We can actually take this outside on some challenging conditions and test if the system is still stable and able to spin. Right? Here is another example of again outside sea sail, trying to spin and walk on gravel or trying to run on gravel. So here are what are some teaser videos of what we are going to build towards. Right? So now I told you I'm going to use learning to go over here, but before jumping into learning, right? Let's try to understand why do we need learning. Right? So when we started as a lab, we had no experience with quadrupeds. Right? So the first thing at the start of the investigation was, well, let's take what exists and study what the failures might be. Right? So we started our investigation with an existing model-based controller, and this controller was the standard controller which comes with the mini cheetah. Right? And what we said was, we're going to begin our journey by trying to make this robot anticipate the future. For example, if it sees it can fall into a gap, it should be able to jump over it. Right? And so it needs to use the terrain information to inform its actions. Right? So this is what led to a paper led by Gabe and other co-authors from the lab, and this was in collaboration with Sangbe. So so the setup is simple. So we are saying we want to study agility, but in research, we have to make problems, boil them down to tiny parts that we can make progress on, and then eventually put them all together. Right? So this is our first instantiation of a tiny problem where we want to increase agility. So what we made are these gap worlds. Right? So the robot can observe the terrain, right? And we can increase the difficulty of the terrain by varying the gap width and the density of gaps. Right? And the platform we have is the cheetah, and all the observations are made by the RGBD camera, which is installed on the robot itself. Right? So now let's discuss the action space of a robot. So the action space is the three velocities, Vx, Vy, Vz, and it can also do turns, but only in the yaw direction. We are keeping the pitch and roll to be fixed for now. Right? Then the other part of the action space is deciding when is the robot going to make contact with the ground. Right? So there are 4 feet of the robot, which are again labeled by LF, RF, LHRH, the standard convention. And so the CT variable denotes the contact state of all the 4 legs. Right? And these are binary variables, either taking a value of 0 or 1. Right? So now, given an observation, right, we want to learn a policy which is going to predict the velocity of the robot and where it should plant its feet. Right? Now, this is going to be fed into an existing model-based controller, which predicts the joint positions and velocities at each joint of the robot, right? And then there's a high frequency PD controller running, which provides feedback motor talks. Right? So this model-based controller is existing work, right? We're just taking it as is, right? What we are trying to do is to build the controller which takes in visual inputs and outputs the velocities, right? And this is going to run at 20 hertz. And for shorthand, I'm going to call the velocities and the contact states by the variable AT known as the action. Right? So our goal is to go from this image to actions. So what are some possible options? So one option is, well, given this depth image, I can try to reconstruct a height map. Right? A height map will tell me where the ground is flat and where there is a gap. Right? And then from this, we can plan and predict actions. The trouble, however, is that it's challenging to construct height maps at high speed. And then these height maps can be noisy, and you need to deal with them, which becomes complicated. And there are some other challenges that we will also discuss in the course of the talk. Right? So for now, let's just consider, because we want the robot to run fast, we want it to also plan or execute actions fast. So ideally, what we would want is to go directly from the depth image to action. So we are kind of deleting one module to maybe gain higher speeds. Right? So now we have this policy pi theta. Right? Now one way to train it is to give rewards, and the rewards might be how fast you move and how much progress you make without falling into a gap. Right? And we could train this with model-free reinforcement learning. Right? So I'm going to call this pi theta as the RL policy. Right? Now, this is good for high-speed deployment, but the trouble is training directly from depth images is actually very hard. Right? So we found that training this policy is just very hard. Right? So what do we do now? Well, this is hard to train, but if we had access to height map, right, then what about then? Could we train the policy now? So is it hard because our RL algorithms are broken, or is it hard just because the sensory observations that we are getting, we can't deal with them? Right? So to investigate this, we made this experiment. Right? Now what we found is that if we give height maps as input, we can very easily train RL policies. But now the trouble is we cannot deploy it because we don't have access to height maps. What we have access to are depth images. So what do we do now? Right? So we really want to learn something which goes from depth images to actions. Now the idea we had is, well, supervised learning is much easier than reinforcement learning. Right? Why is that? Because RL has very high variance, and supervised learning doesn't struggle with those problems. Right? So how can we make use of supervised learning to try to learn this policy? Right? So the idea is, well, we can train this policy in simulation, because in simulation we do have access to the height maps. Right? Then what we can try doing is to copy these actions or to clone this policy in simulation itself from depth images. Right? So this is the loss function, which is trying to match the output of the policy on the top with the policy on the bottom. Right? So this we can do with supervised learning, right? Which is also known as behavior cloning, or specifically what we use is Dagger to learn the policy pi theta st. Right? So we are going to use a notation where we call the top policy as teacher and the bottom policy as the student. Right? So teacher has access to some privileged information not available in the real world, but available in simulation. And then we distill it to work from sensory observations available only in the real world. Right? So we're going to deploy this policy. And one thing to note is that this policy needs to be recurrent, because if we are trying to estimate the state of the world, it's good to have a sequence of previous observations. Okay, so how does the model look like? Right, so we take the depth image, process it through a convolutional neural network, which reduces the image to a latent of 128 dimensions. And then we combine it with some proprioceptive information, for example, the body orientation, velocity, joint position, velocity, body height, so on and so forth. Right? Then we also have previous action and so on. Right? Now these get processed to produce the action. Right? Everyone with me in where we are? Okay, so let's keep moving. So now let's look at this action prediction module. Right, so what is this action prediction module? Right, so this action prediction is a 12-dimensional vector. Now these 12 dimensions are composed of, the first 4 are just the velocities, right? And then the next 8 are going to be predicting the contact states of the robot, right? So what we're going to do is, for each leg, we're going to predict its contact at 2 time steps in the future, right? For the left foot, the right foot, and so on and so forth. So our action space is 12-dimensional. Right. Now the next question is, we have defined a state space, the action space. The only thing needs to be defined is the reward function. The reward function is how much forward progress the robot makes. The action should be smooth, and it shouldn't run too fast. Right. So now our problem description is complete. And now how do we train this? In simulation, we generate different gap world environments. So in some episode, it might look like this. Episode like this, right? So these are just different episodes with different gap worlds. So now let's look at, what does our agent do? But to begin with, we're going to make it equivalent to, model-based systems previously where the gate was constrained. The way we can constrain the gate is to say we are not going to set the contact states ourselves, but just set the velocities, right? And the contacts are going to be set by a predefined pattern. Right, so we'll begin with that, and then we will relax this. Right? So now if we do this, what we get is, for example, we did this for a prong gate. What you find is this robot, going over the gaps by adapting its velocity. Right? So by adapting the velocity, it can jump over these gaps. So now let's compare performance. So what I'm showing on the x-axis is the gap width, and on the y-axis is the success rate. Right? So first, just as very basic baselines, what happens if you have blind, trot, and prong? Right? Obviously, the performance is pretty bad. Right? Then, based on some assumptions such as the Rybert heuristic, we can also compute, how well would an ideal trot and an ideal prong perform. And then, this is, what our method ends up getting, shown in solid lines, is the vision prong and the vision trot, right? Yes?
Why does it get clearance? Normally, if you just write an objective like that, then there's no incentive. There's something implicit normally in robustness or something that would require foot clearance. I wonder if did you have to do any extra terms in the cost function to get that sort of foot clearance?
So the robot wouldn't make forward progress, right? It's going to go into the gap. So we did things where we said, well, the robot should not move its feet too quickly, or make contacts very frequently, and that encourages it in conjunction with making forward progress.
Normally, the optimal gate will have skimming contacts unless you explicitly ask for robustness.
Yeah, so we got skimming contacts, and then we added a term which would try to prevent that from happening. Yeah. Right. Okay, now let's go on the real world, see what happens. Okay, I mean it kind of replicates similar behavior. Here is here is another example. Right, so it's trying to jump over these very tiny gaps. Well, in the end it falls. It's not always successful, as you gathered from the plots. But okay, if you look at it, right, we can only cross gaps maybe which are around 30 centimeters. Right? So what should be a good metric for how long of gaps we should be able to cross? Well, it makes sense to look at the robot's actual body length. That the body length is actually 40 centimeters, but we are doing much worse. Right? So how can we have this robot maybe cross gaps which are bigger than its body length? And for this, what we're going to do is to go back to our action space and relax the gate assumption. Right? So now we're also going to predict the contact states of a system. Everything else remains the same. And this is the result that we get. right? So if you now notice, the way the robot is modulating itself is more variable, right? Then we can go, this is another example, again just showing similar behavior but just sped up. Right? So we can now go and see the performance, and what we find is by removing these constraints on gates, the robot can jump over much larger gaps. Right? Okay. So now we can go around 1.5 times the robot's body length. So the good news is this is working in simulation, right? But what about if we try to deploy this policy in the real world, right? So this is one of those demonstrations. So you might be wondering, why are the platforms colored or have stickers? And the reason is initially we were trying to do SLAM, and then we gave up on it. But at some point we were using it. But our camera is looking at depth images. So these stickers are not providing any helpful information, right? They are just there for a historical reason, right? Here is one more example. Here is one more example, right? But over here, if you see, well, it's kind of working in the real world, but these gaps seem to be much smaller than what I was showing you in simulation, right? So what we found is that in the real world, we couldn't cross more than 26 centimeters. Although in simulation, we could cross much larger gaps. For the obvious, you have a question?
Constrained gate, you make the optimization harder, so even for small gaps, you suffer pretty significant losses compared to vision and prong.
Yes, your question is that even for smaller gaps, we suffer a loss.
Baselines that were more conservative in how much they could jump.
Yeah, so this is something which we believe we can overcome, and I will tell you how through a different example. Yes, it's an excellent question. Right. Okay, so why is the real world performance not good? Right. So let's look at what a policy was taking as input. Right. So one thing it was taking as input is the body velocity. Now, how are we estimating body velocity? Well, there is some model that is written to estimate the body velocity, but it relies on the assumption that there is no slip between the foot and the ground. Right? Now, it's possible that we can improve upon it and account for slip, right? But then there are other things which might also be off. At faster speeds, the motor dynamics might be quite different than how they are at smaller speeds, right? And then other factors might be different between the simulator and the real world, right? So how do we go about addressing them? Right, so one strategy is to build each one of them into our MPC controller, right? So we thought that approach would become like a kitchen sink where we're looking at every case and incorporating it. So we wanted to keep things be very simple. So for the sake of simplicity, no other reason, what we said was, instead of using existing model-based controllers, let's see if we can learn a low-level model-free controller. Right? So okay, let's go into that part. So we have our state, and we want to predict actions, right? And we want to do it to maximize a reward function. Right? Now I'm calling this policy as a nominal policy because in simulation you would typically set some parameters, right? So I'm going to train this policy with one choice of parameters. For example, some value of friction and maybe some value of the robot mass. Right? And the output is a policy pi theta NL, where NL stands for nominal. Right? So now let's look at the performance of this nominal policy as we change the friction. Right? So 0.5 is what we train on. If I increase the friction, the performance drops. It also drops on, if I decrease the friction, but that's expected because at lower friction you can't really run too fast, right? But to notice that, if I go away from the nominal friction, the performance is reducing. Now, how do people typically handle this problem? They say, well, how about we randomize the parameters of my domain because I don't know the friction, let me randomize it. So for example, we can randomize the value of the friction, the mass, center of mass, body strength, so on and so forth. Right? And then we can learn a policy. This is typically referred to as domain randomization. Right? So what is domain randomization doing? It's taking an expectation over all the simulation parameters. Right? So okay. So now let's see how the domain randomization policy performs. Right? So what you notice is that the peak performance of the domain randomization policy is actually lower at 0.5, but it performs better at frictions which the nominal hasn't seen. Right? So in some ways what is happening is this robustness versus performance trade-off. Right? So I'm showing a similar plot from another paper, which is showing that if I was to train one policy without randomization, it can perform really well if the parameters match. But as the parameters become different, the policy performance degrades. So why does it happen? Because if you are taking the expectation over here, what you're saying is that I want to be able to run on all possible terrains and find me such a strategy. Right? So imagine if you also have to run on ice and run on grass. What would you come up with? Right? Maybe I'll walk very slowly like this. Right? And I'll keep on walking like this on all terrains. Right? So this is what domain randomization would end up doing, and therefore it gets a performance hit. Right? But the question then becomes is, how do we mitigate the performance hit of this? Right? So one possibility is we can identify a system better. Right? So for example, by doing less randomization. Right? And this might lead to lower performance drop. Right? But again, doing system identification becomes tedious and slow and will require significant human effort. The other option is, could we somehow automatically learn to perform system identification? Right? So if we can learn to perform system identification, maybe the first thing we can ask is, if I had the perfect system information, how good would the policy work? That is, if I were to randomize simulation parameters, but tell the policy what those parameters were, how good would it perform? Right? So consider this again, this policy, which is the teacher policy, because it has access to some privileged information, right, which is the simulation parameters D over here. Right? Okay, and then we are going to maximize the sum of rewards, but now the policy knows the simulation parameters. Right? So let's see, how well does this teacher policy does, and what you notice is that it, unsurprisingly does better than the domain randomized policy, right? And we would expect this because we know the simulation information. Right? So this is our teacher policy. But the trouble is, we can't really go and deploy this policy because we need to know the simulation parameters. So what do we do? Right? So what we want is to learn a policy pi theta, which is working from states S. And because I don't have D, maybe I can try to learn D automatically. Right? So what we want is, that is, ZT. If this somehow becomes close to D, then this student policy will perform similar to the teacher. Right? So now one thing we could do is we can say, well, okay, how can I infer the these terrain parameters? Maybe by my past states and actions. Right? So suppose if I took a sequence of actions, if the friction was low, maybe I would move by a larger amount, right? And if the friction was high, I would move by a smaller amount. So by looking at the interaction between my state and actions, it should be possible to infer these domain parameters, right? So we can say we want to learn this function phi, or f of phi, which maps a history of state action trajectories to a latent z, right? And one way to do this is to say, well, this latent z should match my domain parameters. Now, this is what we would call as explicit parameter estimation. Now, this can both be hard, but you can also, ask the question, is it really necessary, right? And let me illustrate this with an example. Let's suppose we want to apply a force, and the force depends on the friction, the mass, and the gravity, right? Now, if I have high friction and low mass, it's similar to having low friction and high mass, because the amount of force I need to apply is not going to change. So in some ways, these two are effectively the same. Right? So the idea being that we only want to infer what is necessary and nothing more than that. Right? So, so how do we infer what is necessary? Necessary for what? Necessary for actions. Right? So where we're going to do it is to say, well, let the student actions match the teacher. Right? So it's the same idea that we saw previously, where we were trying to learn from height maps to work on depth images. But now we're going to learn this to do online system identification. Right? So we're going to clone the teacher, again using Dagger. Right? So this is going to be my student policy. Now let's look at how it performs. So what we see is that the green line is actually quite close to the blue line. Right? What this tells us is that the student policy is going to be behaving very similar to the teacher. Now this is a policy that we can go and actually deploy. Right? Now there is work from other labs which looks at similar setups. So if you are interested to learn more, you can also look at these papers. Right? So okay, so this is what we have, right? So what we're going to now do is to deploy this student policy. Right? So now let's look at the student policy in slightly more detail. What exactly we have? So we have a robot, right? The state is again the joint position, the joint velocity, and the body orientation, which we get from the IMU. This is my state. Then the actions are joint positions that we are predicting, and we still have a PID or PD controller running, right? Then we have a history of past actions, as we said previously, and it also takes as input the command velocity, right? And the command velocity is going to be in x, y. There's also z. It's vx, vy, vz, omega z, but I'm going to skip vz for now, right? And for shorthand, we're going to use as following, right? And the reward function is, we want to track the velocity. We want the system to be stable, right? And we want the actions to be smooth, right? So I'm going to skip this, but if you're interested, you can look at the paper, for more details. Then, what we do is we train this policy in simulation. So this is showing a run from simulation. This is ISAC Gym. And in 3 hours of compute time, we can collect 100 days worth of experience. Right? So all you're seeing is each of these agents is a different agent or a different episode which is being run. Okay? So now we collect this experience and we learn a policy, and now we want to evaluate our policy. Right? So how are we going to evaluate a policy? Suppose there are some velocities we command and there are some velocities we end up getting. Right? Then for the commanded velocity Vx and the commanded rotation, we can try to measure the error in the linear velocity and the error in the angular velocity. Right? So first let's look at the error in the linear velocity. So what you are noticing over here is the error in the linear velocity as a function on the x-axis is Vx, on the y-axis is the rotation. Right? So what you find is that we are doing well on a small region of velocities, right? But not doing well on large velocities. Right? Similarly, we can look at the angular velocity error. Right? What you find is, well, okay, this agent is not really doing that well, right? Because it is unable to track the command that we are giving. Right? So it can either run or maybe spin slightly fast, but it cannot simultaneously run and spin fast. Right? Now, why is this happening? Right? Let's try to understand this. Right? So this is happening because what we are doing is we are sampling our velocities from some range, say -6 to 6. Right? Now, what this would mean is that for most of the time, the agent is trying to track very hard things. It's trying to track very large velocities. Right? And therefore, it's going to get low rewards, which are inversely proportional to the error, which is going to hinder the training. So somehow, we can only provide harder commands after a robot succeeds its easier ones. This should help. Right? So this motivates why we need a command curriculum. Right? So now what we're going to do is, we are only going to sample things in a range, say between a very small value. Right? And then we want to keep on increasing this sampling region. Right? So the way we're going to do it is we're going to measure the reward both in the forward motion and say the turning motion. Right? So start with easy commands. If I'm able to perform well on this small range, then I'm going to increase my sampling region. Right? So for example, if the reward becomes more than 0.8, let me increase my sampling region, right? Then again, if my reward becomes more than 0.8 on this region, then we again increase it, right? And this is the strategy we're going to follow, right? So this is what we is a curriculum, right? It's a box curriculum. Now we can go back to the same evaluation, and then we can see what happens with the box curriculum, right? So what you find is that as compared to having no curriculum, you see a lot more of the cells covered by green, right? So if it's covered by green, it means that we can track those velocities very well, right? For the box curriculum strategy is helping us be better. Right? So maybe to answer your question that you asked previously, why we were doing poorly on some velocities was because we didn't use any curriculum. But if you were to use curriculum, that performance difference should disappear, right? Now the box curriculum also makes a particular assumption that it's sampling the velocities independently of each other, right? But instead of independent sampling, we could also sample in a way that they're codependent, right? So for example, over here, it's not a box, right? But we can sample it so that we can model the dependence, because if you're going fast, maybe you can't spin that fast, right? So this is what we're going to call as the grid adaptive strategy. And what you find is with grid adaptive, the performance improves even more. So I'm going to skip one slide in interest of time. It's explaining a metric. So the summary being that this is some metric of how well we can track velocity. Higher is better, and the x-axis is the error. So what you find is the grid adaptive is doing the best, right? Now this is something that we have looked at before. That again we can use the same metric to evaluate the domain randomized policy against a student teacher, right? And what we find is that the student that we have learned through both system identification and the curriculum seems to do quite well, right? So now we can try to evaluate the system on the real world itself, right? So if we were to command, say, a velocity of 6 meters per second, in simulation, it might achieve 5 meters per second, right? But in the real world, it only ends up achieving around 2.5. Now, if we are going to do system ID, like the way we described, we can reach a velocity of around 3.8 over 3 episodes, right? So this online system identification is critical to performance. Right? So this was the MPC controller running on the treadmill at some velocity of 3.7, right? So this is the controller that we had, which could run fast, right? So we could deploy this policy train completely in simulation, and then transfer it on the real system. Right? So this is doing the same thing in slow motion. Right? So we can look at how the robot is moving. Right? Okay, great. Well, I'm going to skip this outdoor dash, and I'm going to skip some of these things because. So I mean, the other good thing is that as opposed to previous agile systems, which are maybe evaluated in some limited settings, now we can go and evaluate them in in almost the wild, right? In the sense we can take it on different terrains. For example, over here it's spinning on ice. Then we can compare the MPC controller on the left, which is trying to climb this set of gravel, and at some point it starts struggling and it stops. This is our controller trying to perform the same action, right? And it manages to recover. Right? So here is another example where you might trip, right? And then similar with the controller that we have, right? Well, here is something which happened unintended, right? So it kind of encountered, this yellow wire, right? So it seems, that it managed to, be robust and stabilize itself. But if I stopped here, this would be cheating because, this is what happened afterwards. it did fall, right? So it did manage to overcome the inertia, but it did fall, and then we became interested, why is the system falling, right? So, we turned out what happens is, if you give a command to the robot to just stand still, this is what it does. It cannot stand still. So if it is running, why is that? I mean, because in training, the standstill command is not given that often, right? So, so what the hypothesis was, maybe you want to make a network be more expressive. So over here, the dimension of Z was around 8, and the system, couldn't stand still. Now, if you were to put the dimension as 16 and then give the same command, it's as is, right? It, doesn't really, end up moving. So we think, the failure we had, we can potentially overcome this, right? Then here is another example, where the system, the knee kind of gets stuck at some point as it is running, right? Because, something goes bad in the knee joint. So if you see one of his leg, it's not functioning properly, right? But the system, still is able to adapt itself, right? So, until now, what we have discussed is, control design. And yes, a question?
You said it's able to adapt itself. Was it actually adapting to that damage, or are you just saying that the policy that you trained happened to be robust to a sense of it?
The policy happened to be robust, but the policy is also taking in the previous states and actions to estimate its latent, right? So in some ways, it's a matter of semantics, right? I mean, it is adapting on the fly, but it never saw like motor failures. What it saw was different motor strengths in the randomization. So it has learned how to deal with different motor strengths, right? So that's what is happening over here, right? So, okay, so what we have seen now is maybe the control design and, some notion of how we can use perception to jump over gaps, right? But what about hardware design, right? I mean, that's also an important component, right? So what we said was, well, these feet make point contacts. Well, imagine, trying to walk and run without ankles. That would be horrible, right? So what we are doing now is, trying to give new feet to this robot, right? These feet are inspired by prosthetics. And, because we're using a model-free strategy, we can easily incorporate and try to co-optimize them, right? So this is, a project with Gabe and Lara and John. And so in some ways, what we are doing is, a full stack approach where we are able to work at all levels of the stack simultaneously, right? So I guess I'm running out of time. I greatly overshot with what I thought I would be able to cover. So I'm going to, maybe, skip, a part of it. Right, so, so what, we presented was, full stack approach, which can go from control, perception, and hardware, right? The next question is, can we apply this thing to something very different, right? For example, over here, spinning a pen, right, or doing some kind of a dexterous manipulation task, right? So now, unfortunately, I don't have time to describe you how this works, but it is the same idea of doing student-teacher learning. And what I'm going to jump directly is to the results, right? So let's look at, what we end up getting, right? Oops. So this is, the output that we get from a dexterous manipulation system, right? So this system is trying to reorient objects, and you can pretty much give it any object, in the sense that we are evaluating it on objects that the system has never seen before, right? So here are, some more examples of it, trying to orient different objects to a target orientation, right? Again, so the same paradigm, we train in simulation, we do system ID, and, then we deploy the policy, right? Okay. So, we did the same framework, right? We got the control design. Now we can say, well, does this transfer to the real world, right? So in our prior work, when they tried to transfer their policies to the real world, they required a very, expressive setup to do it. This is not practical. What we want is to work from a single camera, because that is what we can put on our mobile robots. So how do we go and do this? Well, I don't have time, so let me tell you that we are still going to use the same paradigm of teacher-student, but now the student is trained with vision inputs, right? And it needs to be fast. It needs to use past observations so that we can run at 12 hertz, right? So we again train in simulation and then try to deploy it on the real system, right? So let's see what how this looks like. So again, this is the goal, and the hand is trying to reorient the object, but this is happening in a simplified setup that there is a table which is supporting the object, right? So over here, it kind of gets close. Here is another example. Oops. I guess it doesn't want to play, so it's okay. Something is happening, right? And then, if this hand is trying to reorient these objects, someone can come and disturb it, and it remains robust to all these different, disturbances you might make, right? So, what I have shown you now is that we can use the same framework that we had used before to also tackle it from a perception perspective. What about hardware design? Right, this is something we are interested in. So I'm going to skip this part. Oops, right. So this hand is bad for many different reasons, right? We don't have a palm. There is no touch sensing. We don't know how good is the finger shape, and it has very little compliance, right? So we are working on how can we construct an integrated pipeline for making the hand design and the touch sensing, right? So, and the next thing was, can we automate the design process? So this is showing, some examples where we can automate the design of the manipulator, for a particular task, right? So there are 4 different tasks, and we do co-optimize of design and control. Then we can manufacture these grippers, and this is work in collaboration with Wojciech, right? So in some ways, we are able to use a similar framework across 2 very distinct problems, right? If you have the same framework, same simulator, student teacher training, and the curriculum, right? Now there are tons of open questions, but I'm going to end over here. But before I end, all of this, because I have to still do my 1 minute, which I promised to Alberto about the language, right? The dream was actually, it's just maybe improbable in the next couple of years, but maybe not impossible, is to have this system, say, get me a warm cup of water, and the robot should do it, right? So maybe it needs to go to the microwave and do it, right? Now, maybe this would be solved by GPT-3 or maybe something else, but at the core, what we really need is these skills, for example, to go to the microwave, right? So over here, you have current observation. I want to go to microwave. There's some work being looked at by some students, right? So again, this is trained with same paradigm. We're using model-free RL. Oh no, sorry, this one is not model-free RL, but we also have model-free RL systems to do it, right? And we can go to the top of the leaderboard in the habitat challenge of trying to go to a particular goal location, right? So, okay, semantic navigation, good, but I won't be able to tell you. Maybe I can show you my final slide, which was, what was the dream, right? So I showed you semantic navigation. Then you would need to maybe open your microwaves, refrigerators, and doors. Then maybe move objects around. Then do some in-hand manipulation. Then maybe we come to tool use, right? And then, once we are able to do it, we want autonomy everywhere, which is, maybe quadrupeds, moving around, or doing mobile manipulation, right? So we want to be able to move indoors, outdoors, everywhere, right? So this is what we are focusing on, and hopefully, building these skills, and then we can sprinkle some language magic, and hopefully, get to here, right? So with that, I'm going to stop.
Yeah, thank you for the nice talk. I enjoy it. So I think your student-teacher framework works broadly and effectively. But in the core of it, the problem, we know that there is a very distinct patterns trot versus just a slow walk or jump. I'm just wondering how such drastically different patterns can be effectively applied, and how's that teacher student framework really works to adapt it to such a different cases. That's all that depends on the environment, right? So it seems to me many things that need to be learned, but looking at the possible patterns, very different patterns, how the robot can actually find the reasonable one. Can you make a comment on that?
Yes, so great. So if I understand correctly, the question is that the robot might have to do different things, right? Sometimes it needs to crouch, and sometimes it needs to jump, and sometimes it needs to go left. So how would the student-teacher framework work?
Right.
In that spirit, right?
Right.
So what we're going to do is we're going to train with some pre-specified things the robot can do, which can be very big, right? So it can involve jumping and crouching and moving left, right? And then at test time, given the particular environment we are in, we need to infer the one which is the best, right? And the way this is learned is because in simulation you're learning by trial and error. So you're trying out different combinations given an observation, right? So you learn that in the simulation. Then in the real world, you try to find, well, what was in the simulation which is similar to what I'm observing now, and then get the appropriate skill based on that. So essentially, think of it, if I could try all possible combinations, then at some point I will stumble to a solution, right? So if I could collect lots of data, that would happen. But we cannot collect that much data, so we want to make that data process be more efficient. Right? So that's where the research goes in, that how can we learn more efficiently from simulation so it can learn to choose the right skill.
Thank you. So there's no fundamental, the difficulty dealing with the discrete and the patterns and such.
The fundamental difficulty is how much compute we have and how efficient we can make our systems to be.
Thank you for the talk. I have a question about the teacher and student framework, such that I think is it one possible limitation of the student policy is that its upper bar is defined by the teacher policy performance. So I was kind of curious whether there would be an algorithmic improvement that we can make to make the student policy to even perform better than the teacher policy.
So so this is something that we were trying to investigate. If that can happen, I think Gabe had some good hypothesis. But in some ways, so because the student is using a sequence of observations as inputs, right? And it has less crutches in some ways, right? Because it is not given all the ground truth information. So it's possible that it may learn to generalize in new ways that the teacher doesn't. But the framework as such doesn't require that to be necessary. So I think it's a good question, but do we need it? The answer is no, right? So that's what I would say.
Hello, thanks for the great talk. I just have one question about the system ID student policy. So the student policy takes the input as the inferred domain parameters. And I was just wondering, can it capture how confident is your domain inference, parameter inference? So for example, your inference could be inconfident if there's not enough exploration, or you just done some exploration, but the data isn't good. So you might have unconfident in your domain knowledge. So in that case, is there any way that it can capture those, or is it just assume that accurately the domain knowledge?
So you mean for the student policy, right? You're saying that if it does, some bad actions, then it may not be able to estimate the
Yeah.
terrain properties, right? For example, right?
Yeah.
So that's a valid concern. So what is happening is the distribution shift between the teacher and the student, it is not happening right now because we are training on a very broad range, right? But for example, if you're doing manipulation, right, if you don't touch the object, you can learn nothing, right? So you still need to go and touch the object, right? So what you would do if we run into these problems, then what you would do is you would try to explicitly estimate how much information we have, and then maybe explore if the information is less,
I see.
right? So that's something we have not done yet, but could be an interesting direction to look into.
Gotcha. Thank you.
Thank you for the wonderful talk. I had a question about the efficacy of the system identification procedure. So like the MPC could have failed for a lot of, in a lot of ways, but one of them is the model error of the underlying model that you're trying to use to control. Did you quantify how effective the system ID parameters were in trying to estimate what the environment was, in trying to estimate the environment?
Yes, so I had a few slides on it that, so what we're trying to see is that, if you're walking on, say, grass or ice, do the parameters look different? And if you could, maybe, cluster them, how that would look like, right? So it's a preliminary investigation, and the results are noisy yet, so we don't know. But the hope is that they should be able to tell us, or we should be able to classify terrains based on those parameters.
Let me ask you a question about the manipulation case, which you didn't have too much time to present. So in locomotion, you had one intuition. One of the few intuitions was, for example, that a 2D height map would be useful to have for the policy. Difficult to get in the real system, but sort of useful as an abstraction for the student-teacher policy. In the manipulation case, did you get sort of similar sort of realizations, intuitions that there are certain things that it would be useful for the policy to have that are difficult to get in the real system?
Yes, so it's a very good question. So I think the reverse happened in manipulation, right? So for example, when we were doing reorientation with objects, we thought the policy would need the object shape information. What we found is that even without object shape, the policy can do really well, right? So, and then we were like, why is this happening? Why can we manipulate diverse objects without knowing anything about their shape, right? So one intuition is that if I have more fingers, right, then there are more modes in which I can, move the object around. So maybe all I require is the pose of the object, and I can still manipulate it because there are many, many different ways of manipulating. So what that has led us is to investigate, what we're calling the over-parameterization hypothesis in manipulation, which is that with more fingers, the control might actually be easier than having fewer fingers, right? So, that's one. I'm not answering your question directly, but saying what we observed. Then, other than that, so what we found useful in manipulation was things like knowing the fingertip positions, which we don't know based on the joint encoders, or they can be inaccurate. Same holds true for velocities, right? Because we are differentiating the positions to get velocity, so that can become noisy. So if we provide fingertip positions, velocities as part of the state, as privileged information, that substantially helps in training. So think of it like the end effector locations, having access to that instead of just the joint positions. So that is what we found to be useful.
Thanks. Any other questions? Any final? All right, excellent. Thank you, Pulkit.
Thank you.